Good morning or good afternoon. My name is Oliveira. I am a PhD student, and today I'm going to present the work called Microstructural Characterization of an Ancient Iron Bridge in Brazil. Here you can see the main topics of this work. I will start talking more about the bridge and its history. Then I will talk more about the material and the methodology that I use. I will show the results, the conclusions, and in the end I will give some future work ideas. First of all, I would like to talk more about the bridge itself. So this bridge was built in Brazil between the years of 1864-1865. It has 173 meters and it binds two different cities. It was initially built as a railway bridge, but nowadays with the high amount of cars that we use, the bridge suffered some modifications and today it is also used as a car crossing bridge. Here we can see a recent video of this bridge, and just like this one, we have many other bridges and structures all around the world made with the same type of ancient material, and it's really important to understand how this material behaves because we are still using those structures, so we need to keep them safe. Also, this material was manufactured a long time ago when we didn't have the knowledge and the technology that we have today. So this material doesn't match the international standards that we use. Also, it is known that this type of material suffers a degradation process that has an impact on its mechanical properties because it can modify the microstructure of it. So the main goal of this work is to make a correlation between the microstructure and the mechanical properties of this type of material. For this study, we use two different profiles, and here on the first picture, you can see the position of profile P1 and the position of profile P2 on the bridge. First of all, we analyzed the chemical compositions of profile P1 and profile P2, and later, with the results of this analysis, we made a thermodynamic analysis using the software thermocalc to analyze the impact of the chemical compositions on the precipitates inside the material. After that, we used the light optical microscope to analyze samples from profile P1, both longitudinal and transverse illumination directions, and using the software ImageJ, we were able to analyze the images and quantify the inclusions and the grain size of this material. We also used the scanning electron microscope to analyze the microstructure of samples from profile P1, again both longitudinal and transverse illumination directions, but here our focus was the inclusions and precipitates inside the material. We also used the energy dispersive spectroscopy to analyze the chemical compositions of those inclusions. And finally, we did a computed microtomography on samples from profile P1 to analyze the distribution of those inclusions inside the material and to quantify the volumetric fraction of those inclusions. Looking at the chemical composition obtained, we can see that both profile P1 and profile P2 has a low amount of carbon and a high amount of elements like sulfur, phosphorus, and nitrogen. These characteristics are specific of an ancient material called Pardal iron. And here on the table, we can see the chemical compositions of other structures made with the same type of material, like the A.F.O bridge, the Belfort bridge, and some other historic buildings and viaducts. Looking at the chemical compositions of all the structures, we can see that all of them has a low amount of carbon and a high amount of phosphorus, for example. But when we look only at the amount of phosphorus, we can see that it differs for each structure, showing that this is not an homogeneous material. As it was expected by the composition analysis, here we can see that both profile P1 and profile P2 has a high amount of precipitates rich in nitrogen and phosphorus below the temperature of 400, and this is due to the low solubility of those elements on the ferrite. And those precipitates, they can embrittle the material and elevate its hardness due to the precipitation hardness. In accordance with the chemical composition and thermodynamic analysis, the material presents a high amount of inclusions and also big slag inclusions, as we can see on both images. And this is due to the manufacture process of this Asian material called Pardal iron that was mainly manual, so the workers weren't able to remove all the slags, resulting in this type of microstructure. On the transverse direction, the inclusions are rounder, more like a dot, and on the longitudinal direction, the inclusions are elongated due to the lamination process. On the samples that were etched with nitrile, we were also able to observe this ghost structure. In literature, this structure is associated with phosphorus and non-phosphorus rich regions in the ferrite grain due to high cooling rates. So there is an heterogeneous distribution of these elements inside the matrix due to the low solubility of phosphorus in ferrite. We also analyzed 120 images with different scales to obtain the amount of inclusions inside the material. And we found values between 5.22 to 5.88%, but with high dispersion. For example, a maximum value of 20 and a minimum value of 2.78. And this shows once again the heterogeneity of this material. And here on the second table, there are some values from literature where we can also observe a high dispersion between the results, but here for different structures. The last analysis using the optical microscope was the grain size of this type of material. We obtained a value of 5.07 for the G grain size using the international standard ASTM E112. We used the scanning electron microscope to analyze the inclusions and precipitates inside this material. On the left image, we can see a big slag inclusion and that there are different compounds inside of it. On the next image, we can see some straight lines inside a few ferritic grains. Those lines are known as Newman bands and they are usually found in ancient irons rich in phosphorus that were cold worked. With a higher scale, we were able to observe this great amount of intragranular precipitates inside the ferritic matrix. And using the results of a thermodynamic analysis, we believe that these precipitates are rich in nitrogen and phosphorus. We could also observe that those precipitates have a non-homogeneous distribution inside the matrix, and this can be the main cause of the ghost structure that we saw a few slides ago. In literature, this same type of precipitate is commonly found on Pardal iron. To characterize those slag inclusions, we use the EDS to obtain their chemical composition. On this slide, we can see the results for two different points. Both of them are rich in phosphorus and sulfur, which is in accordance with the chemical composition for the material. The last analysis was the computed microtomography. So here on the left image, we can see the 3D body of the sample analyzed made by the software using the data provided by the equipment. And on the right image, we can see the inclusion distribution inside the sample and some 2D images. On this analysis, we obtained a value of 3.63% of inclusions inside the material. And again, we can see that their distribution is not homogeneous. And also on this analysis, we need to cut the edges of the samples on the images to avoid errors on the simulation. With the chemical composition and optical microscopy analysis, we were able to verify that this material is a Pardal iron, rich in elements like sulfur, phosphorus, and nitrogen, and that it also has a great amount of coarse inclusions. With the thermodynamic analysis, we saw that this material also has precipitates inside its matrix, rich in phosphorus and nitrogen. Those elements can embrittle the material, and that's the reason why, despite it have a low amount of carbon, this material have high values of hardness, yield strength, and ultimate strength. Using the scanning electron microscope and the EDS function, we saw that those slag inclusions are again rich in elements like phosphorus and sulfur, which is in accordance with the previous analysis. And finally, with the images obtained by the computed microtomography, we were able to see the non-homogeneous distribution of it inside the material. And this direction of those inclusions and their distribution of it has a high impact on the impact resistance of this material and on its strain properties, showing again the high anisotropy of this material. as some future work ideas, we have heat treatments, so we can evaluate the influence of this heat treatment on the precipitates rich in nitrogen and phosphorus, and how it is going to affect the mechanical properties of the material. We also want to use the transmission electron microscope to evaluate those fine intergranular and intergranular precipitates that we saw on some images. And at last, we would like to characterize the microstructure of this material using non-destructive techniques, because we won't always be able to have samples from those structures. So it's really important to characterize it using non-destructive techniques. Here there are some references that I used. That's the end of my work, and I would like to thank you for your time.